we're going to turn our attention to a kind of a specific subgroup of discrete variables and discrete probability distributions. That is the binomial probability distribution. Now, binomial probability distributions, simply put, binomial, we have two words or two things, two items, and so this incorporates anything that we can kind of define as one of two possible outcomes. So any experiment where we can say it was either this or that was going to happen, and those are the only two outcomes possible, right? So in the most straightforward, we can flip a coin, it's heads or tails. We can say this is either true or false. You could think of making the shot or missing the shot, getting a hit or not getting a hit. Now, we don't want to, that's a yes or no there. You can't have single, double, triple, home run. That's no longer binomial. But if you can summarize it and say this is either a hit or it's not a hit, or you got on base or you didn't get on base. You either win the lottery or you don't win the lottery. So as long as we can summarize it as either happening or not, or yes or no type of a question, or a true or false, and this can be a broader. The experiment could be shaped in other ways, or listed. The outcomes could be listed other ways. So what do I mean by that? If we roll a die, just rolling the single die, a D6 die, it has 6 faces. That, if we don't consider it anything other than what face comes up, that's not a binomial. But we could divide that and say, all right, I want to know if that was a 5 or 6, or so that's like one outcome. Maybe we could write that as greater than or equal to 5, and then the other one would be, that's not even the right way to, so less than or equal, no, okay, we'll flip that around, greater than or equal to 5, or less than or equal to 4, right? And now we have two outcomes, and so it's binomial. Okay, so we can take other information or other scenarios and kind of, what's the term, pigeonhole them into a binomial scenario. And again, that's one of the reasons why binomials are used quite often, is because a lot of times we can fit certain certain experiments into that and use some of these mathematical techniques. It turns out that although now while we first enter into these calculations, they're going to seem a little cumbersome and annoying, and why do we have to go through this whole big process of the combinations formula? But it turns out that this is it ends up being a more efficient or an easier mathematical method than what we've been talking about in general, right? So our general process of discrete probability distributions, as to, so far we've basically listed out all of the possible results, figured out which outcome they would fall into, and then summarize that into kind of an outcome table, the probability distribution. Okay, and so while we're working with flipping a coin a few times or rolling 2 dice, that's manageable, although we didn't even write out all 36 of the 2 die rolls. It gets quite cumbersome and computationally heavy even for computers. Whereas the binomial distributions, the binomial formulas we're working with here, while they are little painstaking at the start, we'll see that we can quickly get to the results, at least relatively quickly. And in fact, when we turn and calculate the mean and the variance, it's snap of the fingers quick. It's very quick. So yeah, so it's a very useful way to outline a probability here. So just when you come across binomial distributions, we often talk, the terminology is often referred to as success or failure, so you'll see that in literature and whatnot, the number of successes or the number of failures. And in fact, when we look at our formulas, we'll often refer to it as successes or failures. Now, that doesn't necessarily mean what a success is is dependent on how you set up the experiment, right? And so it's probably most natural to count, a success as a made shot, but oftentimes we also think of, did you get the disease? Yes. That's oftentimes referred to as a success. So success doesn't necessarily mean the positive outcome. It's more of the affirmative to kind of a yes in that, to the answer of the yes/no answer, the yes/no question. So we have when we're setting up a binomial distribution, or how do we know if we can have this experiment be a binomial distribution? Well, there's 4 things that we need to kind of have satisfied for it to fall and be a binomial distribution. And your book has these, but we'll kind of talk through them briefly here. So again, what we've been talking about, there's only 2 possible outcomes. Okay, so it's 2 outcomes. Now, they need to be mutually exclusive. Okay, so we can't have, greater than or equal to 5. Whoop. It's me trying to talk in, right? Greater than or equal to 5 and less than or equal to 5, right? That's not mutually exclusive. We can't have that. We also need, so everything else, well, let me not skip ahead. So we need 2 outcomes. They need to be mutually exclusive. The number of trials is fixed and known. Okay, so what do I mean by that? Well, oftentimes when we turn to a binomial distribution, and maybe I should have said this at the forefront, but we know. So, for instance, take the 70% free throw shooter. We know that they're going to make, if they take 1 shot, they're going to make 70% of them, or they have a 70% likelihood of making that shot. Same with the flipping a coin, right? 1 coin flip is 50%. But what's more interesting is if we can incorporate that into a broader experiment and say, okay, what if you take 5 free throws? What are the chances that you make 2 out of the 5 or 3 out of the 5, right? And we've talked a little bit about this already. So, for instance, we've even calculated what's the chance that you make all 3 of 3 on a free throw, or 0 out of 3, or 0 out of 2, right? So we've done some of the extremes, right? Because we know we can just multiply, what did I say? The 0.7 times 0.7 times 0.7 gives us the likelihood of making all 3. But what the binomial probability distribution, it allows us to fill in the middle gaps, right? So again, go back to the 5 free throw example. What's the likelihood that you make not just 0 or 5, but what about all of them in the middle, right? So we will be able to build a probability distribution that incorporates all of these middle points, and maybe there's a small little chance. We'll know how to calculate exactly what this is. Okay, but we'll be able to build that full distribution. And so. But for that to be true, we need to know that the number of trials is fixed and known. Number of trials. So a trial being 1 shot here, right? So in our 5 free throw example, there are 5 trials. Now, you may already notice this, but we've done this exact thing actually with the coin flip, right? So a coin flip is a binomial, and so the very first discrete probability distribution we did was the number of heads or tails. I think we said number of heads in 3 coin flips, and that was a binomial distribution, right? We knew the chance of getting 0 and 3, but we also were able to calculate 1 and 2, and we were able to do that because there were only a few different results to walk through. Okay, and again, we could treat this free throw example like we did with the coin flips. It's just that the outcomes would be enormous, right? Because you could, if you want to think about how many ways there are to make 2 out of 5 free throws, there's quite a few. And in fact, that's a lot of what our work does here, is that we crunch that with the combinations formula. So we kind of bypass that whole listing out all of the results. So the third thing that needs to be true here is that the independent, or sorry, I'm jumping ahead. The probability of success is the same for each trial. Okay, so every time you flip the coin, it's the same probability. Every so if you're thinking about 5 free throws, you don't tend to get better or you don't learn along the way and then you get better. So that might break down if you are learning some new skill, right? We assume that people that are shooting free throws have kind of learned the skill at a certain level, but if you were trying something new, right? So if you're trying a new pool shot and the first chance, you might have a much lower chance than the fifth one. Okay, so the probability of success, again, however we determine which outcome is success, the probability of success is same for each of these. And then lastly, the trials are independent. That's what I was almost jumped up to number 3. So what this means is that the outcome of one trial doesn't impact the other trials, right? So if let's say you've hit 3 free throws in a row, you don't have any better chance of making the 4th. Okay, and so we often like to think of shooters getting hot or cold. I think in the data it tends to show that that's not true. We're just kind of seeing that in the past. But if that were the case, if you thought that in this scenario they were independent. So one place this might break down is going back. We talked about getting the disease or not getting the disease. Well, if the disease, so that's a binomial situation, but if your experiment that you're interested in is 6 people in a household, how many people are going to get it? Each of those people have a yes-no situation, but if it's a communicatable disease like COVID, then the fact that one person, so whatever happened to the first person, so if they got the disease, it changes the likelihood of the other members having had the disease, or if they didn't get the disease, it lowers the chance, right? So they're intermingled, and so if 3 out of the 4 first ones have it, you can assume that there's a much higher chance that 5 or 6 also have it. So that would fail this independent trials. Okay, and so these 4 items we need to make sure are true if we're going to use the binomial probability kind of shortcutted math, right? A lot of what we're doing here is shortcut math, and if these break down, then these math things aren't gonna hold. Okay, so so we can find the probability of each outcome. The probability of X, right? That's what we've been after in any of these discrete probabilities. But we can find that with, and there it is. So the binomial probability formula, again, looks very gross, and we'll walk through this in another video. Whoop. That's good timing, so we'll just blow that up. And so the probability of X is equal to, and here, I know this looks very gross, but we have the combinations formula. Right, we've done this in chapter 5, and then what's new here is that we have pi raised to the power x, and then 1 minus pi raised to the n minus x. Okay, so a lot going on here, but let me just tell you that pi we are treating as the probability of success in each trial. So for our free throw shooter, we've said 70%, so pi would be 0.7, and so 1 minus pi is 0.3, right? So there's this balance. As pi goes up, 1 minus pi goes down, and vice versa. And those are raised to the power of the number of successes or the number of failures, right? So n minus x is going to be the failures. And so a messy formula when you just glance at it, but note that we're prepared and ready to tackle all the parts of that. So we'll come back and walk through that in some more videos, and then I thought I had that pulled up ready to go. Oh, here. Okay, so just to highlight lastly, why are we so interested in this? Well, as we'll get to in some videos, but notice how simple these equations are. The mean of a binomial distribution is simply n times pi. Okay, that's much more simplified than our summing up x times the p of x and that whole process. And even more simplified, the variance of a binomial distribution, n times pi, 1 minus pi, right? And again, what you notice there is we're not dealing with having to calculate the deviations from the mean. So we skip all of that math. So really, I know there's a gross combinations formula up here, but you should be excited that perhaps you won't have to always calculate deviations from the mean to get to the standard deviation. So that's really the benefit here. The quick ways to summarize the outcomes. So we'll be back with some example videos walking through all three of these formulas.